So hi everybody. So it's lecture 9. Okay. Let me make this a little thicker. Okay. So 9. And so last time, what did we do? Well, we continued our discussion of number theory. And last time we finished proving the fundamental theorem of algebra. And then we started talking about division modulo m, so the notion of an inverse modulo m. And then we looked at the special case of inverses modulo a prime, which led to Fermat's little theorem. Enable. Okay. And in computing the inverse, we had to use some stuff we did last week, like we had to use Bézout's theorem, and we had to use the Euclidean algorithm again. And we're going to use all this stuff again in this lecture. That's why I'm reviewing it. And remember, Fermat's little theorem is the statement that if p is a prime, then a to the p minus 1 is congruent to 1 modulo p if it doesn't divide a. So in this lecture, we're going to do 3 things. So one is I'm going to talk about, we did one more thing, which was we saw how to use inverses to solve linear congruences. Namely, an equation that looks like ax is congruent to b mod. Is there something wrong? Because I'm seeing a lot of people leaving the class. Is there something wrong with the screen?
I thought so too, because at once it was like from 60 people, it went like shot up to like 120 people and then it like started getting lower. I don't know.
Yeah, bizarre.
I think one person there's like 30 of one
Yeah,
person.
that's what I saw.
Oh, there's 30 of one person?
Yeah, when I was checking out the names.
Okay. Well, then I guess, okay. I guess it makes sense that the number of that person is decreasing, but okay, fine. So
yeah, there's like 50 Rebecca Grants.
I see. Okay, fascinating. So anyway, in this lecture, I'm gonna talk about the Chinese remainder theorem.
Hey, Keel, if we have some questions on like the logistics of the midterm, should we wait until after lecture to ask?
I'm going to get to the midterm at the end of lecture. So yeah, I will have a section at the end where I'll talk about the exam. Then I'm going to talk about an application of all of this stuff that you see on the screen, the stuff that we do in the last few lectures, to something we actually implicitly do every day, which is cryptography. And then finally, at the end, I'm going to talk a little bit about how to study for the exam and just take any general questions about the exam as well, as you just asked. Okay, so let's start by talking about this Chinese remainder theorem. So we talked about how to solve a single linear congruence modulo m. The Chinese remainder theorem, which is an ancient theorem, I suppose, developed in China, tells us how to solve a system of linear congruences. So, for example, let's look at a simple system. We want to find a number x so that x is congruent to 1 mod 3. And now it's congruent to something else, 3. No, actually, let's start with something a little simpler. Congruent to 0. Oh, sorry. Congruent to 0 mod 5 and congruent to 0 mod 7. So there's a reason why I'm looking at this 1, 0, 0, but this is a particularly simple system of congruences modulo different numbers, which in this case all happen to be prime. So I'm looking for a number that's divisible by 5 and 7 and has a remainder of 1 modulo 3. Any ideas on how I might find such a number? I admit it's not very easy.
You could just look for successive multiples of 5 and 7.
Okay, so a good starting point is to so maybe one idea is, well, it's easy to satisfy the second two equations because 5 times 7, this satisfies the equations 2 and 3, right? Okay, but 5 times 7 is actually is not congruent to 1 mod 3, right? So this is 35, which is actually congruent to 2 mod 3. So any ideas on how to manipulate this to get it to solve the first equation?
Multiply it by 2.
If you multiply by 5 again, wouldn't that work?
Okay, right. But okay, these are all good ideas, but basically I want to turn this 2 into a 1. So any ideas on what I should multiply this by?
Well, we'd
The
want to,
inverse.
yeah, which would
2
be
inverse, yeah, good idea, right? So now multiply by 2 inverse, which actually happens to be 5. Maybe that's why you came up with the 5.
Yeah.
Or what am I saying? That doesn't make any sense. No. So 2 inverse actually is just 2 in this case. The inverse of 2 is itself mod 3.
Just 2.
And now you get that you get a number. So x equals 70. And this now satisfies all the equations, right? So x is congruent to 2 inverse times 2, which is congruent to 1 mod 3.
Where did you get 70?
I multiplied this number 35 that I initially guessed by 2 inverse, which happened to be 2, and that's 70. So I fixed the first equation by multiplying by the inverse of the right-hand side. Okay, so you can do this in general, actually, right? So in general, you can actually always solve something like this. So in general, you can solve x is congruent to 1 mod, let's call it m1 all the way up to x. Oh, sorry. Let me. Yeah, okay.
Wait, that's 2 to the -1, not 2 to the 7, right? In the
Yeah, that's 2 to the
top.
-1. That's
Oh,
the
okay.
inverse of 2 modulo 3, which happens to be 2. So let me make that clear. Yeah. Good point. Okay, that's not much clearer than fix this. Okay. So in general, if you have a congruence like this, you can modulo a bunch of numbers where the first right-hand side is 1 and the other ones are 0. Whenever these numbers are relatively prime, pairwise relatively prime, just by taking x equal to the product of all the other numbers so let times its inverse modulo m, so times, let's call it I, where I is the inverse of m1 through m start m2 through mk modulo m1. And this inverse always exists because these numbers are relatively prime. Okay, so you can always solve a system like this where exactly one of the right-hand sides is 1 and the other ones are 0. So any questions about this observation? Right, and then the proof of this is obviously x is congruent to 0 modulo m2, m3, m4 because of this product, and it's congruent to 1 modulo m1 because of this inverse. Okay, so now the Chinese remainder theorem says that you can always do something like this, right? So if m1 to mk are pairwise relatively prime, then the system of congruences x1, sorry, not x1, just x, is congruent to a1 mod m1 congruent to a2. So now the difference is they may not be 0 or 1 mod m2 all the way up to xk. Has a unique solution in the interval 0 all the way up to capital M minus 1, where M is the product of all these numbers. And the proof is pretty close to what we just did, actually. Wait, what? I've run out of paper. Okay, let me add some more. Okay. So let's see the proof. So proof is let x equal y1 times capital M1 times A1 plus y2 times capital M2 times A2 dot 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 all the way up to yk times capital mk times ak, where I haven't defined these capital Mi, so let me define them. Where capital Mi is this product M divided by little mi. So it's a product of everything except the ith modulus. And yi is its inverse, is the inverse of mi modulo little mi. Okay, so this is just generalizing what we did in the previous example. Okay, so now what's the key point? So observe that X is congruent to, okay, this whole thing. And then there's a particular term in here, the ith term. Is congruent to this number modulo mi. So observe that for every I.
Sorry, is the last line supposed to be YIMIAI or is it little mi?
Oh yeah, sorry, YIMIAI. Yeah. Okay. But now what's the punchline? Well, the punchline is that modulo little mi, all of the capital MIs, except for the ith one, are going to be 0. So they all just disappear. So this is congruent to YIMIAI modulo little mi, since mj, well, is divisible by little mi, right? When j is not equal to I. It's a product of all the little mi's except the ith one. So all the terms vanish except the ith one. Okay, but now I claim that this is actually just AI mod mi. Why is that?
Because yi and mi are inverses of each other.
Yeah, I
mod
chose
mi.
yi to be the inverse of capital Mi. So this is congruent to AI modulo little mi as desired. Okay, so this is actually just the existence part. And uniqueness by now is kind of, it's the same as all the other uniqueness arguments we've done. I'll just skip this. It's just, it's easy. It's like the uniqueness proof in the division algorithm. Okay, so there's a very explicit theorem. It basically shows you what the solution is. You form this product, and you look at these numbers you get by moving one modulus at a time. You compute these inverses, and this just gives you the solution. So that's the Chinese remainder theorem. Any questions about the statement or proof?
May I see the statement again?
Yes. The claim is this has a unique solution.
Got it.
Okay. So that's the last sort of new theorem we're going to learn in number theory. And what I'm going to move on to now is an application of all this stuff in cryptography. Okay, so what is cryptography?
Wait, can you scroll up like 1 second, like to the proof page?
Yeah. So this proof is also in the book, by the way.
Okay, thank you.
So cryptography is this sort of very broad field which deals with how to send information in a way that's secret. So, you want to send some sensitive information across the internet or some other communication channel, and you want it to be, you want to transform it in a way so only the intended recipient can read it. And if somebody else sees it in transit, they can't figure out what it says. So this is something we actually kind of interact with every day. And one motivating question is, suppose I go online and I want to buy something on Amazon. There's this question of how do I send my credit card number to Amazon without hackers, securely, without somebody just looking at what's coming out of my Wi-Fi and just reading it. So the answer to this is something called public key encryption. And the reason this is particularly fascinating is I don't have any agreement with Amazon beforehand on some kind of common password or something that I can use to that I can use to make this transaction. So instead, the metaphor in public key encryption is the following. So there are two people. There's Amazon, and then there's me, Nikhil. And the metaphor is that Amazon sends me an open lock. Okay. So suppose Amazon could send me an open lock without the key. Well, then what I do is I take my credit card number, I put it inside a box, and then I use this open lock to lock the box. Okay, it's a terrible picture. You can see that my drawing skills are really bad. And I send Amazon back a locked box. Okay. And now Amazon sitting over here has the key to this open lock that it sent me, and it unlocks the box and takes my credit card number. And nobody else can open the box because nobody else has the key. Now, obviously,
So only
this,
Amazon.
excuse me?
So only Amazon has a key, so you couldn't even open it yourself?
You can't even open it yourself.
Oh.
But this is good enough for you to send them your credit card safely, right? You know your credit card. You don't need to open the box once you lock it. So this is called public key encryption because I don't need to have the key in order to lock the box. That's the beauty of it, right? That somehow there's this digital analog of an open lock that I don't even need the key, but I can still lock stuff and send it to Amazon, and only Amazon can open it. As opposed to private key encryption, where I would somehow need to share this key with Amazon. So anyway, now I'm going to explain to you how this works, and it's based on all the stuff we learned in the last lecture. This is due to Rivest, Shamir, and Edelman. It's called RSA encryption. Okay. So the goal is so at a high level, the goal is to send a message M, which is a number, and the way this is done is in three steps. So let me say the number, the message is a number in some set 0 through n-1. So for example, I'll tell you what little n is in a moment, but my credit card is an example of a number. Of course, you could send any other information by encoding it as a number if you want. Okay, so how do we create this locked box? So there are three steps in this protocol, the RSA algorithm. So I'll show you the steps on the left, and then I'll do a running example on the right, just to illustrate them. Okay. So step one is called key generation. And this is done by Amazon. This is the step in which Amazon, constructs this lock-in key. So in this step, what does Amazon do? So you choose two large prime numbers, P and Q. So on the right-hand side, here's a running example. So I'm not going to choose big prime numbers because I want to be able to write them on this page. So the primes in my running example, the primes are going to be 7 and 11. In practice, the primes would have like hundreds of digits. It'd be really big prime numbers. Okay. And then the other thing Amazon is going to do is going to choose an integer e. Oh yeah, so I'm going to choose these two large primes, and I'm going to let n be the product. Okay, so now n is 77. Now I'm going to choose an integer e between 0 and n minus 1, such that it's relatively prime to a number phi where phi is not the product of the primes, it's the product of the primes minus 1. Okay, so there's a lot going on here. There's a bunch of different numbers, right? So there's a number as p and q. Then there's a product n. Then there's this e, which stands for encryption, which you'll see in a moment why. And it's especially chosen so it's relatively prime to this number phi, which is related to the product of the primes, but it's a product of the primes minus 1. So in this example, I have phi is 6 times 10, which is 60. And e, I mean, there are many choices for e. I'm going to choose e to be, in my example, what did I choose e to be? I chose e to be 7. Okay, so I have to generate these 5 numbers. And now the open lock, which is called the public key, consists of 2 numbers, n and e. So this is something that Amazon is just going to publish this on the internet, saying, hey, if you want to send me stuff, here's your open lock. So this is the analog of the open lock. And then the key, which is called the secret key, looks like it's the same. It's P, Q, and E. Okay. Now, what's the difference between the public key and the secret key?
We factored n into the 2 primes that it's
Exactly. So the reason the secret key has more information than the public key is it contains the prime separately, whereas the public key only contains the product. So the underlying principle. So the underlying principle in cryptography is that it's very hard to factor large numbers. So it's easy to find n from P and Q. So it's easy to multiply 2 numbers and find the product, but it's hard to factor n into its primes. Okay. So that's why if you just give me the open lock, I can't just produce the secret key because it's not so easy to factor a number with 500 digits. Okay, so I haven't told you what I'm going to do with this yet, but that's how you generate the open lock and the key. Any questions about this definition so far? Okay, so now for step 2. Step 2 is encryption. This is the step where I put something in this box and lock it with the open lock. Okay, so for the encryption, I have a message M, which is this number in the set 0 through n minus 1, which is a big number because these primes are big. So this is the message I'm trying to send. So let's say my credit card number is 2. I wish my credit card number was that short, but let's say it's 2. So how do you encrypt this message M? So the ciphertext, this is the crypto speak for the locked box containing the message. C is you take your message and you raise it to E modulo N. Okay. So it's kind of weird. But notice that I can do this if I have the open lock, right? I take my M, I know N and I know E, so I can compute M to the E modulo N. So in my running example, the ciphertext C is going to be 2 raised to the 7 modulo 77. So I'm going to do this in a bunch of congruences. And okay, so what is 2 to the 7? That's 128. And so the remainder in this case will be 51. So C is just 51. Okay, so step 1 is key generation, step 2 is encryption. Yeah. The only operation here is raising a number to this encryption key E modulo N, which is all contained in the public key. Okay, so you might be a little bit concerned that in general, if I have numbers with hundreds of digits, how would I do this? So how would you do this if I gave you some really big numbers?
Using a strong computer and the algorithm like fast exponentiation.
Yeah, you'd use repeated squaring, which is the thing you learned 2 lectures ago. So repeated squaring in practice. So repeated squaring is actually something that your computer is doing all the time. Okay, so and then you send this across the channel, you send it across the internet, you send the ciphertext, that's what you send. And the last step is decryption. How do you recover the message from the locked box? So this is how to open the box. So how do you, really the question is, how do you reverse this process of raising M to the E? And I mean, can you even do it? It's not even clear you can do it, right? So this is where this is a really beautiful idea. The decryption step, what you do is let D, so choose D to be an inverse of E. Modulo phi. It's kind of not obvious that why this is relevant. I'll explain it in a moment. I guess I should say congruent too. Or yeah, let B. Or yeah, actually, yeah, no, we define the inverse as the one that's smaller than phi, right? The positive one that's smaller than phi, that's the one. So let's just say let B be E inverse modulo phi. And to decrypt, compute the decrypted message M prime, or maybe that looks like a 1, so let me use a different letter. So let's call it M hat, which is you raise the cipher text to the power D modulo N.
M equals to C to the what?
C to the D. So you computed the inverse of E, which is the encryption, this encryption key. And now to decrypt, you just raise the ciphertext to another power, namely D. So in this numerical example, let's just see what we get when we do this. So in the numerical example, the ciphertext is 51. So first I have to compute an inverse of 7, right? So the first step is you have to compute 7 inverse modulo phi, which is 60. How would you do that?
Without theorem,
Excuse me?
like without.
Yeah, just use
theorem.
Bézout's theorem, right? So using Bézout or the Euclidean algorithm, you find, I won't do the computation in front of you since you've done it in the homework. You find that D is 43. Okay, so in particular, it turns out that 43 times 7 is congruent to 1 modulo 60. Okay, and now let's compute m hat. This is going to be this number 51, the ciphertext raised to the 43 modulo n. Okay. And now, how again you do repeated squaring, which I'll skip. And if you do this, you get that this is 2. Now, this is by no means obvious. Okay. I skipped the calculation, so maybe it wasn't as stunning. But if you do the calculation, you actually get back the original message M. Now, let me now prove that this always recovers the message. Okay, but before I do that, so the theorem is that for every message, m hat equals n. In the Erlov scheme. So that's theorem 1, and then really the more interesting theorem, which we won't prove, but if you take a cryptography course, we'll prove it. Theorem 1. Theorem 2 says any algorithm which can recover M from C without knowing the secret key. So another way to put it is using only the public key. So basically it's saying if there's any way to break the locked lock, can be used to factor integers. Efficiently. Sorry, my handwriting is getting pretty bad. But theorem 2, okay, we won't prove this. What it's really saying is that there's no way to break this lock. Because if you did, you'd be able to use that algorithm to factor integers, which we believe is impossible. So theorem 2 says that this is secure. Theorem 1 says that this works, that you can at least recover the message after doing this crazy modular thing to it. So any questions about the description before I prove theorem 1? This should say efficiently. I haven't defined efficiently, so that's why this is okay. Maybe I should put the whole thing in quotes, since this is sort of more of a computer science theorem, which maybe you learn about if you take, I don't know, CS 170 or 270 or something. But yeah, so let's focus on theorem 1. Any questions about the scheme or theorem 1? So there are 3 steps in the scheme.
Is the point of theorem 2 just saying that if you had some other algorithm that could somehow get by the complications of the, the scheme we just outlined, you could just might as well do the scheme itself?
Exactly. No. The point 2 is saying that there's no way to break the scheme other than by factoring large integers.
Oh, got it. Thank you.
And we believe that's hard. We haven't proven that, but nobody has found a way to factor large integers. So in other words, the only way to recover the message from C is to know P and Q. There's no other way to do it. That's kind of what this is saying. In quotes, I'll put this since we have it's not a formal statement.
So we would be in a lot of trouble if someone came out tomorrow and say, hey, I found a way to factor large integers, right?
Yeah, so this is like a serious thing because it turns out that if you had a quantum computer, which is something a lot of people are working on, then you could factor large integers. So this is part of the reason why people are spending like lots of time and money trying to find ways to build a quantum computer. And there's also a whole area where they're trying to find encryption schemes that don't rely on factoring. But so far, nobody knows how to factor large integers, and maybe we never will, but maybe we will. I don't know. So this is not saying it's impossible. It's just saying that this is breaking the scheme is as hard as factoring large integers. So if you believe that's hard, then you believe the scheme is secure.
So can you factor a large integer and get our credit card number?
Yeah, so if you have an algorithm that factors 500-digit integers, you can get everybody's credit card number. It would lead to a complete, at least, breakdown of capitalistic society, because you'd be able to like break into banks, you'd be able to do all kinds of stuff.
You need different primes for different stuff, right?
Yeah, so basically what Amazon does is it generates a new open lock every time it does a transaction. So yeah, you have to, I haven't told you how you choose two large primes and stuff like that. There are ways to do that too. But yeah, every time you do this, you generate new primes, you generate new keys. For every transaction, actually, your browser is doing this. Or actually, Amazon is doing this and sending you this public key, and then you're doing this little computation and sending them back this ciphertext. Okay, so let's prove theorem 1, that at least this weird looking scheme actually is a valid way of communicating a message, which is by no means clear, right? So proof of theorem 1. Okay, so let's just so theorem 1 is yeah, so let's just recall what everything is, right? Let's just write it down again. So there's a lot of numbers floating around. So I need to prove that m hat is equal to m, right? So m hat is c to the d, and c is m to the e, right? So observe that m hat is c to the d, which is m to the e to the d, which is just m to the ed. Okay, and what do we know about E and D? So D, how did we define D?
They're congruent to 1 modulo phi.
Yeah, so ED is congruent to 1 modulo phi. And phi here, by the way, let me just remind you, in this box, phi is p minus 1 times q minus 1. And what does that really mean? that means that E times D is equal to K times phi plus 1 for some integer K, right?
I believe your
Thank you,
screen is
yeah. I think it's frozen.
Oh, man. Okay, back in a second.